In this video, we're going to be talking about differentials, or what some people say Leibniz notation. And some people might say, what are differentials? Differentials is just basically you can say that differentials is going to be the derivative of each piece. All right, let me try to clarify that. Let's go ahead and look at the objective. The objective is state what dy is dependent on in differentials, write the differential form for dy, and then finally use differentials to estimate real world situations. Let's go ahead and look at what they mean by differential. Let's pretend I'm given the function y equals f of x. So this is the function that I have. And what we've learned is we've learned to take the derivative of this, and we say y prime is going to equal to f prime of x. And that's what we've always been doing, right? But some people say, well, I don't use that notation. I use this notation. Dy dx is going to equal to f prime of x over here. So differentials is just going to be these pieces here, that piece and that piece. This is a differential and this is a differential. Basically, it's just saying the part of the dy and the part of the dx. So if I take the derivative of this, like I use this notation now, and if I multiply by dx on this side, what I do to the left, I must do to the right. So I multiply by dx on this side. The dx here and the dx here reduce to a 1. So what am I left with? I'm left with dy is equal to f prime of x times dx. So we can honestly say that the dy, right, is really dependent on both the x and the dx. So that's one of the objectives. So what is the dy dependent on? The dy is dependent on the x and the dx. Okay? So now let's go ahead and see how finding differentials is. And you guys say, well, it's not that hard, sir. It's actually really easy. So let's go ahead and take the derivative of this. But remember, we're going to use Leibniz notation. So I'm going to say dy over dx is going to equal to 5x to the 4th plus 37. Now, what I want is I want to leave dy by itself. So what am I going to do? I'm going to multiply this side by dx. Okay? I'm going to multiply that by dx, and I'm going to multiply this by dx. So when I do that, this and this reduce to a 1, and I'm left with dy is going to equal to the quantity of 5x to the 4th plus 37, quantity times dx. And that's it. And I'm done. And you say, well, differential, this is not that hard, sir. No, it isn't. The question is, when they put it in a real world situation like this example, some people says, well, it looks a little more complicated, right? So let's go ahead and let's find out what we have to do in this problem. The radius of a circle increases from r equals to 10 to r equals to 10.1. Now, what a lot of people don't realize is when I give you an initial r and I give you an ending r, that means that you're supposed to be able to say that dr is going to equal to 0.1. In other words, this is the change in r. And it used to be 10, now it's 10.1, so it grew 0.1. So there's a difference of 0.1. So it's really 10.1 minus 10, which is 0.1. Now I'm noticing here that they have dA estimate the increase in the circle's area. So let's go ahead and bring in the formula that we need in order to do this problem. So we're talking about the radius of a circle, and we're also talking about the change in the area of the circle. So I really need the area of the circle. So the area is going to equal to pi r squared. So all I need to understand is that when I do differentials, I'm going to be taking the derivative of the left side by itself, and I'm going to be taking the derivative of the right side by itself. So they're not going to have anything in common. So I'm just going to say the derivative of a is going to be dA, and the derivative of this side is going to be 2 pi r, but I took the derivative of an r, so I have to put dr. Okay, so now we can say that the dA is dependent on not only the r but the change in r. So let's go ahead and plug in the change in the area. Now remember, we're talking about the original circle, and the original circle is going to have a radius of 10. So what I'm gonna do is I'm gonna insert my information here, and I'm gonna put in a 2 pi, and my radius is 10, and my change in my radius was 0.1. So when I multiply this out, I'm going to end up with 2 pi. So now, what is the, now it says estimate the area of the enlarged circle. Now remember, what is the area of the original circle? The area of the original circle is going to be, A is going to equal to pi r squared. But my radius was 10, so it's going to be pi times 10 squared, which is going to give me 100 pi. So the original circle has an area of 100 pi, but the change in the area is going to be 2 pi. So that means that my new circle, my larger circle, the area of 10.1 is going to be approximated to be 100 pi plus 2 pi. And that right there is going to give me an approximate area of 102 pi. So that's what we're getting using differential. Now what is the exact area? All right, well, the exact area, I'm going to come down here and I'm going to say the area is going to be pi, and my radius is now 10.1, and I'm going to square that. So let me take out my calculator here. So I'm going to have to go 10.1. Okay, so let me go, oops. Document here. Let me do a new document. Okay, I'm going to go 10.1 squared. Oops, I forgot the 0.1. So I'm going to go here 10.1 squared. And when I do that, it's going to give me 102.01. 102.01. So 102.01 pi. So if you look at the exact area and you look at the differentials area, what are you noticing? That it's very close. This one was 102.01 and this one is 102 pi. So it's only off by 0.01. All right? And that is using differentials to solve a real world situation. Okay? Now, here's another scenario. The scenario says find me the cube root of 7.97. And we're trying to estimate the cube root of 7.97, and nothing else is given. So you're saying, sir, I have no idea where to start. Well, let's pretend that it's not 7.97. Let's pretend it was just a plain x. Okay, so I really want you to find me the cube root of x, and I'm going to call that equal to y. So what I'm going to do now is I'm going to take the derivative. I'm going to do the differentials here. So I'm going to end up with dy is going to equal to, now this one, before I take the derivative, I'm going to rewrite it as x to the 1/3. So I'm going to end up with 1/3 x to the negative 2/3. But I don't like that negative power, so I'm really going to end up with 1/3 x to the 2/3 power. So this, oops, but I took the derivative with respect to x, so I need to put a dx. Now the dy is dependent on the x and the dx. And now you're looking at this and saying, sir, I still don't know what to do. Well, what you need to understand is you're going to choose something for x, something that we know. So I'm going to say that x is going to equal to 8. Now, why did I choose 8? Well, because I can take the cube root of 8. That's the reason why. So I'm going to take 8. Now, remember, I'm estimating. So I'm saying, let's pretend x is 8, but it's really 7.97. So what is dx? Well, dx is going to be 8 minus 7.97. So 8 minus 7.97, that's going to give me 0.03. 0.03. Okay. Now, some people might say, hey, sir, is it positive or negative? You know, and some people are going to say, well, it's going to be negative 0.03. Okay? And we'll understand because it's below it. So we're really supposed to go 7.97 minus 8. Okay? So let me go ahead and erase this out here. And I didn't have to erase that one, but I'm going to say that it's really 7.97 minus 8, which is going to give me negative 0.03 because it's below it. If it was above it, then my estimate would be greater. So I'm going to now substitute. So I'm going to say, let me change the color here to green. I'm going to plug in, for the x, I'm going to plug in a 2. So I'm going to have 2 to the 2/3. And my dx is going to be negative 0.03. So that's going to give me, well, oops, this is not supposed to be 2, it's supposed to be an 8. The cube root of 8 is 2. 2 squared is 4. 4 times 3 is 12. So I'm going to have 112 times negative 0.03. And that is going to give me what? What is that going to give me? Let me take out my calculator here. And I'm saying negative 0.03 divided by 12 is going to give me, that's going to be a really small number, negative 0.0025. Negative 0.0025. Okay? So now, that's my dy. So what are we going to do? We are going to, let me go ahead and express it up here, all right? So we're going to say that f of 7.97 can be really written as f of x here, all right? We can say x, let me undo here, x plus dx, all right? And that can be approximated as f of x plus dy, okay? So what we're saying is we're actually going to be doing the, remember what did we choose for x? We chose 8. So we're going to say it's going to be f of 8 plus dy, and we already found dy, okay? What is dy? Let me put an approximation here, okay? The f of 8 is really going to be the cube root of 8 plus dy, and we found out that dy was negative 0.0025. Now remember, had we left it as positive, we'd be adding it, and our approximation is going to be greater, so that doesn't make sense. So that is going to equal to, the cube root of 8 is going to be 2 minus 0.0025, and that is going to give us an answer of 1.9975. Okay, so what we're going to do is we're going to check our answer by taking the calculator out. So I'm going to take out my CAS, and I'm going to say the cube root. So I'm going to go the cube root. And I'm going to insert a 3 there. A cube root of 7.97. 7.97 percenter, and it's going to give me 1.9975. Wow, that was very, very good estimate. Okay.